Okay, so today we're going to have a look at the impedance characteristics of the cylindrical coil and of a TMT system made from the cylindrical coil. At first I'm going to show the setup that we've got here and then move to recording the video on the computer screen itself, so we can look in detail at the impedance measurement results. So as we can see here, we've got the normal setup. I'm using the GG8 SAQ vector network analyzer, which I've used in a lot of other posts on the site. Also, I have a dedicated page for that. There is a post there where I look at the characteristics and the setup and the features of that vector network analyzer. So we're going to use that here. There it's connected to the computer, and then the output is connected to the primary of the Tesla coil, cylindrical Tesla coil that we see in front of us on the bench. So just to pan the experiment so you can see what the overall layout is, there's the pair of cylindrical coils. We're going to be doing later, we'll be connecting those via the bottom end of their secondaries to form a cavity between them, so they'll be using them as though they were a TMT system in the near field. They've both got vacuum tube variable capacitors, which are used to tune the primary, and we'll see a lot more detail about the effect that has. We've done previous posts in the past about the impedance characteristics of flat coil, and now we're going to look at a cylindrical coil, and in the future obviously I will be looking at other coil geometries as well, which I'm combining on this first page about the cylindrical coil to give an overview of some different coil geometries and their characteristics and uses. So that shows the overall setup. I'm just going to pan it back round so we get the main view in, and just point out a few things here in the picture. So here is the connection, here's the GG8 SAQ vector network analyzer connected in here into the primary. This is our vacuum variable capacitor in the primary section, and we see the secondary here slides away, so we're going to be doing some coupling measurements as well. So as we vary the distance between the primary and the secondary, we'll look at the impact that has on the results. Obviously I can slide that very far away. Here's the primary coil. We have selected 3 turns. This is a 4-turn primary. We've selected to use 3 turns in this scenario. This is a very similar configuration actually to Eric Dollard's cosmic induction generator. So the design is relatively similar and can indeed be used for those experiments, which I'll be coming on to in subsequent posts. At the bottom end of the secondary here, we've got a wire extension, so we just lower the impedance at that end. So then we're working with a lower impedance and a higher impedance at the top end, so we're looking to resonate that in quarter wave mode. That'll make it a quarter wave resonator, as we would expect to use that within normal parameters and within the type of experiments that we're going to do with this kind of coil. So I think that's everything about the setup. Just gives an overall lie of how everything's connected. We will probably use a load on the end of the TMT, so on the receiver coil at the other end of the bench here there is a incandescent 100-watt load, and we will connect that during the TMT measurements, so we can see the impact that has. That usually lowers the Q of the transverse part of the cavity, and we'll see the impact that has on the results. So I'm going to change now to actually recording the computer screen, and then we'll start actually having a look at the impedance measurement. So this is all going to be about Z11. So the small signal AC input impedance as seen at this point. So that's ultimately what the generator would see. If we had a generator attached, like say for example a vacuum tube generator like this, if we had it attached there, that is the impedance that the generator would see looking into the circuit. I mean, often we will have a matching unit between the two, but that involves that vacuum variable capacitor, and often when driving with a tube supply, then there will be some other matching elements in there as well. With a spark gap generator or an impulse generator, discharge generator or something like that, then obviously we'd have a tank circuit there as well. So understanding the Z11 or the input impedance of this circuit is very important, and this also tells you a lot about the overall, how it looks through the entire system. It's surprising how much detailed information you can get about at least from the transverse side of this experiment, by looking at the input impedance with a vector network analyzer. And in subsequent posts, I'm going to have a look at the transfer characteristics of this. So Z21, so that is input applied here and throughout, as both on this side of the Tesla coil and on the other side of the TMT system. We can look at the transfer characteristics, and that's known as Z21, and we'll be using the same vector network analyzer to do that. But that's to come in subsequent posts. So I'm going to set up now, and then we'll continue looking at the measurements on the computer.
Okay, I've transferred over now to recording the computer screen. We've got the VNWA DGA SAQ software open, and on the bench where we saw the cylindrical coils, I have just got the secondary coil, one secondary coil. I've removed the other coil system and the primary, and we've got, so they don't interfere with the results, and I've got the secondary coil series connected. So in other words, I've series feeding with the bottom end of the secondary coil connected to the output of the vector network analyzer, and then the earth then returning down to my RF ground. So in effect, the secondary coil is sitting on top of the vector network analyzer, and this allows us to do a very accurate measurement of the free resonation properties of the secondary. So before we get into that on the screen here, we're starting at 100 kilohertz and we're going up to 25 megahertz. So we're doing a wideband scan here. So before I start making this scan over 25 megahertz, I'm just going to do a calibration. Bring up the calibrate menu, start with the short, connecting the short to the output of the vector network analyzer. Now the open circuits. And finally the load, 50 ohm BNC termination. Just going to run that again. Yeah, it's consistent at the beginning. Okay, so that was the calibration. If I now run calibration sweep, yep, unwrap phase is just whipping round. Let's just move the marker into position, and we see there it's about all the markers coming out around right on 50 ohms. So that's fine, the calibration is fine. So I'm going to remove the 50 ohm termination. I'm going to connect the series fed secondary coil again. There we are. Going to just rescale a little bit. Put the phase at 20 per division. I'll make it larger. And this is how it looks now for the secondary coil. We got that series resonance. This is the fundamental down here at the bottom. Just zoom in on that. Put that right in there. So 1.95 megahertz. We've got that series resonance at low impedance point, the 115.92 ohms. Just doing that and come up to the top here. Scale this, actually let me auto scale the blue one so we can see. Okay, so there's the top of the peak. We're going to position marker 2, the top here. Zoom in there. Look, I'm going to put that around about the center of that peak there. Okay, so parallel point 2.09, serial point 1.95, and the parallel point 2.09 megahertz. So the fundamental resonant frequency of that coil. And as we can see, we've got second harmonic, third, fourth, fifth, sixth. So that'll actually also be the second odd harmonic. Let's bring marker 3 in. We'll just have place it there at the moment. 6.36. Yeah, so this is the quarter wavelength resonance here. This in effect here would be the second even harmonic, so that would represent half wavelength, and then we've got 3/4 here, 3/4 wavelength at this point here, second odd harmonic, and that's at 6.36 megahertz, and then 5/4, 7/4, 9/4 as we go up. It shows quite typical for a high Q resonator. We can see that the quality factor, even on this scale, is very high. Is what we would expect for a cylindrical free resonator over this kind of bandwidth. Okay, let's go to looking at the narrow band scan. I'm going to go up to, I normally go up to 5 megahertz here. And so I'm going to single sweep that. That will focus in much more now on the fundamental. Again, 1.95, 2.09. I really just scan that so that I can save it. So I'm going to export that. Actually, I'm going to do magnitude and continuous phase. I'm going to do that over 5. Save that. Good. Okay, so that shows us very clearly the series point, series resonant point here, and there's obviously got a corresponding parallel point here. I will say more about that in the write-up. Now, let's get that marker just on the top there so we can see. There. Okay, so 2.08 megacycles, 14.4 kiloohms. Okay, so that describes nicely our free resonant properties of the cylindrical coil, at least that's sufficient for what we need now. I'm going to now pause this video, and I'm going to bring the primary, I'm going to take the secondary away, I'm going to bring the primary in, and then we look at the properties of just the primary on its own. Okay, I've taken the secondary away, I put the primary in its place. Obviously the primary now is parallel fed, as it would be driven by the generator. I haven't changed any of the calibration, although I am going to put this sweep back to 25 megahertz. Got it calibrated over that range at the moment. Okay, so put that back over 25, so our calibration remains consistent. I have disconnected the vacuum variable tuning capacitor, so now we are just driving the primary coil, and I've got 3 turns tapped in. So this is a multi-tap primary with 4 turns maximum. I'm using the outer 3 turns I've got connected. And we'll take a sweep of that. Okay, so let's just auto scale over this side. It's quite big. Let me just bring so we can see the top of that. Okay, that's fine. Okay, so here we don't, as is consistent with a coil like this in effect. This is a lambda by 2. It's a half wavelength coil. It's got no tuning capacitor on it, so obviously it's predominantly inductive with very small parasitic capacitance. We're down in the picofarads, and this is normally what we would expect to see. This impedance peak and the phase change will be right up the top here. So there will be a phase change that corresponds with the self-resonations of this primary. We could go up higher to have a look at that. We'll have to, if I take this up to 50, obviously we are relying on the background generic calibration. Let's just see if we can do that. There it is. Okay, so there is the phase change up here. Let's just auto scale that. And let's take the marker. So marker 1 we've already positioned. We've got that primary impedance peak, 27.4 kiloohms at 7.7 megahertz. Let's bring marker right up to here. Top there. So that self-resonant phase change is taking place at 40.2 megahertz. That's its self-resonance. So that's the primary, the inductance of the primary with a very, very small parasitic series capacitance in the picofarads, self-resonating up at just over 40 megahertz. And of course we've got this massive offset here with the parallel peak here, because we've got such a big imbalance between the inductive part of the reactance and the capacitive part of the reactance. So in that case, we see very large offset between parallel point, the serial point at 2. Obviously we have a secondary peak down here as well. That's quite normal for a self-resonating primary coil like this, and this is with 3 turns on it. If I were to adjust the tap point, let's just have a go at that. So I've taken 1 turn out now. It's now 2 turns. We try that. It made some difference. So it's pushed that down to 39.4 from just over 40, and we has pushed this up as the inductance has fallen. Inductance has fallen, so and they see they've moved towards each other. So now at 9.5 rather than 7.7. So this parallel peak has moved up this way. This the phase change from the self-resonance has moved down as they gradually coming closer and closer because of difference in the reactances. Obviously, if the reactances were balanced, then so the magnetic and dielectric fields of induction were balanced, then those two could come together, and the parallel impedance point would be equal to the phase change. But that's obviously, we're very far from that condition. So I'm actually just going to save that. So it's a useful result. So this is the primary only. Parallel fed. That's 50 megacycles, and it's two turns, no C primary. So in other words, no primary tuning capacitor in there. That's our characteristics for this scan. Save that in as 3. Okay, then I'm going to put it back. I'm going to put the taps back to 3 because that, I think, is where we would expect to normally drive this. An optimum point somewhere between 2 and 3. The calculation for this coil equal weights of copper with the secondary is 2.4 turns. So between 2 and 3 is probably the most optimum point to drive this both transversely and longitudinally. Let's just sweep that again. So they both move out. It should have moved back down to 7.7. Oh, it's right at the top. I got that right at the top. That's good. And that right back there so we can see that we've got back to the same point, which we have, to 7.7 and 40.2. And we could even take that third one and see where we've got that secondary parallel point. Zoom in. It's a little bit difficult to adjust if you don't zoom in. Get it right at the peak. And that's at 43.1. Okay, so that's what we would expect for a self-resonating primary without tuning capacitor. I'm just going to save that for the write-up as well. No, not that one. Export data. Magnitude continuous phase. So this is now 3 turns. Everything else remaining the same. 3, 4. Okay, all right, so now we've got to this point, I'm going to reconnect the parallel tuning capacitor. I've got that currently disconnected from the circuit. I'm going to plug that in now. It's the advantage of having these high voltage 4mm terminals, so that you can connect these things relatively easy, which is good in the experimentation. And I've got the tuning capacitor fully out. So that would be less than 20 picofarad load that that's placing on the circuit. So let's just do another scan. Okay, we see that loading. Okay, so everything's shifted down slightly. Now here in the situation, they didn't move further apart or closer. We've put a loading onto that coil, external loading, so we're adding an additional parallel capacitance to that resonance circuit, and we notice that everything shifted down slightly, which we would expect as we start to load additional capacitance. It's literally only the open capacitance of the vacuum variable capacitor, which in this case is about 20 picofarads. And we see the marker was where we were at 1, and we have moved down. Let's just get that to the top there. There we are. 6.9, and the phase change has moved down. Phase change has moved down to 40.1. Okay, so very small change by adding parallel capacitance there. So what I'm going to do is I'm actually going to, I want to put this in real time, so we're going to have a look at the sweep characteristics. Sweep characteristics, time per sweep is only 5.4 seconds. I'm going to reduce that, right? Actually, I'm going to reduce the points right down to 512. That will allow us to reduce the sweep time down to 0.68 of a second, so we can do some more real-time measurements. We may need to recalibrate. Let me just close that, take a sweep again. You see it's much quicker than it was, and it's also slightly shifted. So it's not far. Just reposition those so we know what our starting point is. Okay. So that was our starting point, 6.9 megahertz, 20.7 kiloohms at the parallel point. At the phase change of the series point, 40.1 megahertz, 3.1 ohms, and then we'll also set that top there, 42.7. Okay, so we're all set, and we're going to put that into a continuous scan now. So it'll just keep taking scans, and I'm going to start slowly winding that capacitance, parallel capacitor in, so the capacitance will start rising. So it's already, you see the marker from point 1 is already falling away as the peak shifts down. Phase is shifting, very, very small changes at the moment. Look. You see it gradually moving down. Phase is proceeding downwards, parallel point, everything is proceeding downwards as we load more and more capacitance onto that parallel resonance circuit. Let's just back off a little bit there. We got effect from a higher harmonic there. Let's just go back. Okay, so that's where we were. And so I wound the capacitance out again. I wanted to show that point where we start to get interaction with a higher harmonic. Okay, so I'm going to start winding the capacitance in, increasing the capacitance again until we see the entrance there. At the top end of the screen here, we've got this second phase change occurring here from a higher order resonance, a higher harmonic. Keep winding that in. So that's completely consumed. And we see the parallel peak is still moving downwards. Where we have marker 1 was where we originally started at 6.9 megahertz. 2 and 3 were where we originally started for the phase change, and we've moved down considerably now. If I add an additional frequency marker, we can see where we're currently at. Put that right on the top. I mean, the reason it's changing is because we're in real time. Still scanning to 4.9 megahertz. So we've now moved down from 6.9 to 4.9 as a result of additional capacitive loading. If I look at the position of the variable capacitor, it's probably no more than about 60, 70 picofarads that's been loaded on there. We're going to keep going down. You see the change is rapid now. As I load that capacitance on, that phase is working its way very quickly downwards in frequency. Parallel point is also moving down. You see also that higher harmonic opening up again as it's no longer consumed in interaction with the lower harmonic. Keep moving downwards, and you'll start to see how this parallel point here, eventually that will get down to the kind of frequencies where the secondary fundamental resonant frequency is, and that's going to then form classically when it's tuned, we know as the lower and the upper resonant frequency of these types of Tesla coil. It applies to the flat coil, it applies to the cylindrical coil. Actually, all Tesla coils in this kind of geometry sets with a primary and a secondary with a coupling, non-zero coupling up to about half, will display that same kind of characteristic as the primary resonance circuit and the secondary resonance circuit interact. And that's not that the primary resonance circuit is at the same as the secondary. It's not designed in that way to where they're both resonating at the same frequency, at least not in this design. I mean, they can be set like that, but in this case, we are just loading capacitance on that parallel tuned circuit in the primary, and that will affect the tuning of the entire Tesla coil system, including the secondary. So we're still winding that capacitance down. If I have a look at the capacitor, we're still only about a third in, so we're probably at around about 200 picofarads now. Keep coming down. You see the parallel resonance going, is almost beating as it goes through maxima and minima, comes up, now it's coming up, right up. Q is good at that point, and then recedes. It goes through that cycle, recedes, now it will come up again. You see the higher harmonic largely staying where it is, up there now. Phase change still moving downwards. We're progressing quite slowly. The variable capacitor is probably about 300 puff now. As it keeps marching down. We'll do a narrowband scan of this also later so we can see more accurately what's happening at the lower end. Still winding it down. Okay, we're probably at around about 600 puff now. We're about halfway over the adjustment range of the variable tuning capacitor. And if we just have a look, let's just get that marker 4 in there. We bring it up to a peak. Right up there on an IQ point. Bring that marker in. Right up to the top there. So marker 4 is now 1.9 megahertz. So that's already, that parallel point is now equivalent to the parallel point that we saw on the secondary. It's about 1.95. So they are in equivalent place now. Now, of course, when the two are coupled together and interacting, obviously we're going to see that upper parallel point from the primary is going to push on the secondary and move that whole tuning of the fundamental resonant frequency of the Tesla coil into the classical lower and upper frequency with the phase change from the wire length of the secondary in the center. But we're going to, at the moment, carry on winding down the primary. See how far it really goes. Right, that's fully closed. So it's about almost 1300 picofarad. This peak, let's just pause the scan for a moment. We have a look in here, put that right at the top. It's very sharp, so it's difficult to get it there. And that's at 1.6 megahertz. So in other words, that parallel point loaded with 1300 picofarads of parallel capacitance across the inductance of the primary coil is going to push that peak right down to 1.6 megahertz. So in other words, we are fully within a tunable band for the secondary coil that we're going to use. I mean, 1.6, we're down in the medium frequency band. Now it's right in the medium wave section. So we've got a full range of tuning from a medium wave up to the 80 meter amateur band for that. And even actually a little bit higher than that as well. You see the phase change here now. Let's add another marker. I want to leave the original markers. Let's add another one here, and that phase change now is sitting at 57.8. So still fairly high, well above the fundamental region for the secondary. So what I'm going to do is I'm going to wind this out again now. Actually, I will first of all save. I will take a save of this, export the data, next continuous phase, and we only so full CP, and I know from measurements this is 1300 puff, 50 megacycles band, everything the same. Okay, so I'm going to wind, I'm going to set this back into continuous. I'm going to start winding the capacitance up now. I'm going to do it a bit faster now so we see it change more rapidly. That's it. Reducing the capacitive loading. Everything is shifting back up rapidly at the end there. Very fast. Right back up. Until we've reduced that loading now. That's that fully open. So it's probably just 10, 20 picofarads at that point. We wound over the whole range again, and we have come back to where we started. So 1, let's just stop trace. 1 is right at the peak, 2 is at the top, 3 is at the top of that peak. That's where we started from. 4 and 5 are left at the minimum points. So those were the minimum points. So the range that we went from was 1 is 6.9, and it landed up at 4 at 1300 picofarads, 1.6. That was the range of our tuning of that primary parallel peak. The phase change shifted from 2 to 5. That was from 40.1 megahertz down to 7.8. Obviously, the gap between the parallel peak and the phase change is also reducing as the balance is better between the reactive components within the resonance circuit. Okay, good. So that shows the full characteristics of the primary when tuned over its full range and with three turns engaged there. So what I'm going to do now is I'm going to pause this, and I'm going to put the going to reduce the band. So I'm going to take it down from 50 megahertz to 25 again, and I'm going to bring, well, actually I'm going to take it down to 5 to start with. I want to look at the fundamental region, and we're going to bring the secondary coil back now in close proximity, or coming into close proximity with the primary, and start to see how those things make a difference. So I'm just going to take a pause now and bring the secondary coil back in. Okay, so I've put the secondary coil back on the bench. It is now 1 meter away from the primary coil, so they are actually in line, but separated by 1 meter, as though I had drawn the primary away from the secondary at a meter distance. I've still got the capacitance fully wound out. I'm just going to do a single sweep. Did that run? So everything looks exactly the same. Nothing has changed. We can't see the secondary at this stage. The coupling will be too low, so it will be very close to 0, and it's too far away from the primary for us to be able to see that reflected through into the input impedance sweep. Okay, so what I'm going to do now is I'm going to, let me put it on continuous. I'm going to wind the capacitance down, or capacitance in, and increase the low capacitive loading as we have done before. And I'm going to put it somewhere round about the mid region at about 700 puff. So I'm going to put it, just lock it there. That puts it in the middle of its operating band. This was the band I would normally expect it to operate around about 500 to 800 picofarad, depending on where you're tuning the secondary operation to, or the total system to. And I'm now also going to reduce the bandwidth of the scan here. So I'm going to pause that for a minute. I'm going to go back into 5 megahertz narrowband scan, and we've already got calibration for that. Do a single sweep. Okay, so there we just see the primary. We don't even see the phase change off the top here. Remember, that phase change was sitting up there somewhere around about 7-8 megahertz. So now we just see that primary peak. I'm going to put it back in continuous. Okay, so it's just a primary on its own. Let's just change the vacuum variable tuning a little bit just to see how that moves around. So yeah, we can see that that's all changing. Let's put it on a peak there. That's fine. I'm going to get rid of some of these. We don't need these. Some of these higher ones. They're all off the end here. So 2, there's 1. Let's put 1 on that. It's the only feature that we've got at the moment. Let's just pause that. Have a look. Okay, that'll be fine. Okay, so we're at 1.95 megahertz. Okay, good. Well, that's interestingly where I'd set it is almost exactly the same as the fundamental resonant frequency of the secondary. So I'm going to put this back on continuous scan now, and I'm going to gradually shift. So that's scanning. We've locked the tuning, put marker 1, and I'm now just going to gradually, I'm going to shift the secondary. Remember, the secondary also has a wire extension at the lower end to keep it in quarter wave mode. I'm going to move it down towards, we're going to see where, sliding it now towards the primary, we're going to see where we start to see some kind of feature change as a result of the coupling coefficient increasing and the secondary coming into the sphere. Okay, so we can see something starting to develop there. At the moment, let me just check the distance that we've now moved down to. They're now at 70 centimeters distant. So bring it down further. Further. That feature's starting to grow there. We can see a phase change is starting to come into. They're now at 50 centimeters, so half the distance. And the primary's just starting to interact with the secondary at a very small degree. So coupling coefficient would be very small at this stage, probably around about 0.01. Bringing it closer. That phase change starting to grow now, and we also start to see the impedance starting to change now down here. That phase change, that be most likely attributed to the wire length. That's the fundamental resonant frequency of the secondary, at the phase change at which that occurs. Let's just put that in there, to 2.21 megacycles. That is what we would expect. And they're now at a distance of just over 30 centimeters. Bringing them closer. As they start to come into the sphere. The phase change is getting quite rapid now. Let me just pause it there. And 20 centimeters now apart. We start to see there's the emergence. That's the wire chain, that's the emergence, that's actually the upper. That's the upper resonant frequency, and this one is becoming the lower now. You see one from the primary, one from the secondary. Keep bringing it in closer. Phase change becoming strong now. Starting to, you see the splitting, forming the lower and the upper resonant frequencies very clearly. Okay, that coupling coefficient now is probably around about between 0.1 and 0.2. They are now separated by only 5 centimeters. bringing them further so they become fully interlocked. There, now they are completely together. So the primary is now inside the secondary. Coupling coefficient will be quite high, almost up more than 0.5, probably a little bit more. And you see the splitting of the upper and the lower frequencies is very well developed. We've got that phase change from the overall wire length. That started off, that was down at 2.21, it's now quite high. It's moved up higher, 2.6. Put that now back down at 2.21. Okay, so what I'm going to do, we're actually over-tuned here. So we're over-coupled and we've got too much loading capacitance on here. So we're going to balance this up now. So I'm going to increase the spacing between the two. I'm going to bring it back to an optimum point, coupling coefficient around about 0.2, and I know for that system that means spacing between the coils withdrawn by about 5 millimeters. I'm going to come out a little bit further. That's around about there. Okay. Let me just adjust some of these things so we can see it more clearly. Let me just pause it for a second. Put it at 1,000. Let's I did click that a lot. Adjust the phase slightly, so let's make it 60 degrees per division. Now we can see everything very clearly. Go back to continuous sweep, and I'm going to balance up this coil. I'm going to wind out the capacitance, too much capacitive loading on this coil. So I'm going to wind it out until we reach the balance point. Adjusting. See, we're taking loading capacitance out of the primary coil. That's affecting both the secondary and the primary. Now we're getting more to a balanced type of point. There. Now we've got the secondary and the primary in balance. We've fully developed the lower and the upper resonant frequencies. So here's the lower. Let me just pause that for a moment. Yeah, just make sure we're reasonably balanced. Okay, so let me just put our markers now. So this is the lower resonant frequency. That's almost right on the right place. Put it in the center there. 1.94. Let's get the serial point, the phase change, right in the middle. Let's actually look at the impedance end, see where the minimum impedance occurs, right on that phase change point there. Okay, that's at 2.32. It's not bad since we designed this coil to be 2.3 in this position. So that actually came out very close from our original design in the previous posts. We arranged the quarter wave resonant frequency that will actually reflect the wire length or the phase change in this region, and that's at 2.3. And this is 2.32. It's pleasing when those things work out the way you originally intended them to. Let's just get this sorted out. There we go. Right, so there we are. So the lower resonant frequency is 1.94 megahertz. The wire length phase change from the secondary is 2.32. and the upper resonant frequency is 2.69, corresponding obviously with their parallel impedance and series impedance. And that obviously affects where we would tune that into what kind of generator we were using. If we were using a linear oscillator or a linear amplifier, we'd want to be tuning more on points 1, 3, depending on whether we are tuning at the upper or the lower frequency we want to drive at. Obviously with a spark gap generator or an impulse generator of that sort, we want to have very low impedance. We're tuning towards the lower impedance point, so we get high oscillatory currents or impulse currents in the primary circuit. So that's a nice balance. Let's see if our balance is maintained. Do another sweep. Yes. Well, let's put it on continuous. That's a nicely balanced point. That is a good place to drive that cylindrical coil at. We've got a reasonable balance between the electric and magnetic fields of induction. The Q is good, and we have a range of different driving points here depending on our matching to the generator and where we want to actually drive. Probably the optimum places to drive this are 1 and 3. Telluric transference of power I find works very well at 0.3. You can use 1 or 3, but 3 I've found you can pass more through to the receiver. Okay, good. What I'm going to do now is I'm going to show the effect. Now we've got that balance point. Actually, I'm just going to pause that. I would like to save that result. Check the balance. Yes, that's reasonable. Those are at the points. That's at the low point. Okay, I'm going to export that information. Want that part of the write-up. So this is now primary plus secondary, parallel thread, 3 turns. Okay, now I'm going to need to measure that. So I'm just going to bring a LCR meter in. This is a UCOL U822C I use for all the measurements. And we see how much capacitive loading we've actually got on there. Disconnect one of the connectors and that'll measure 585.5 picofarad. So it was nice and stable. So 585.5. This is a over 5 megahertz scan. So this is, I'm just going to also add, this is balanced. Oh yes, let me add here 5 centimeter spacing. That's for the primary and secondary, where I've found it to be round about optimum. Pop that in there. Save that. Bring our LCR meter out of the way and let's replug the tuning capacitor in, and we'll just take another sweep just to see that we are still where we expect to be. Yes, we are. It's good. Everything's very stable. Put that back on continuous. All right, so now I'm going to move slowly the secondary away from the primary. We see how this balance point changes. Okay, so I'm moving it away already. See, as I move away, the separation between the lower and the upper resonant frequencies is reducing. So the lower is moving to higher, away from marker 1, this point here, and the upper is moving to a lower away from 3. So this separation, this splitting band is reducing. Interestingly enough, the balance is remaining reasonably well between the lower and the upper. There's a good balance between the primary resonance circuit and the secondary resonance circuit. Keep reducing that some more. I'm just going to check the distance between the coils now. That's 10 centimeters. So we've gone from 5 to 10 centimeters. I'm actually going to pause that. I want to move the markers. I want to save this result. But basically we see that let's put this back on the bottom. Bring this close in there. There we go. Okay, so now the lower resonant frequency has moved to 2 megahertz, upper 2.55. Phase change from the wire length is very marginally changed from 2.32 to 2.27. Okay, let's just store that. So that's as a result of 10 centimeters spacing. Everything else remaining the same. Interestingly enough, the tuning was good enough that we maintained the balance. The balance has been maintained. Let's just do another sweep, make sure we're still in that. Yes, we are. Let's continuously sweep. I'm going to move further away. Start moving further away. We're going to see the frequency splitting continue to collapse. Balance is staying okay. So swinging a bit further now. I'm going to bring that out to, I want to bring it to about 15 centimeters between the two. That was a balance point. That's 15 centimeters between the two. And again, they are reasonably balanced. Yeah, oh, that's actually good. Okay, all right, again, I'm going to bring the markers in. We see again that essentially the upper and the lower frequencies are collapsing onto each other. In other words, the effect from the primary and the effect from the secondary they're not interacting so much. The coupling coefficient's gone down, and therefore they are essentially becoming more independent circuits, and therefore not influencing each other to the same degree. We also change, of course, the amount of energy that we couple between them. There's an important balance between it being a free resonator and the amount of energy that we can actually couple. And that's something we considered in the previous post about coil geometry. Okay, let's put this back on here. It also shows how important it is when matching the type of generator that you're using. That looks pretty good. Let's just check it. Yeah, pretty good. Let's put it in the middle. Okay, so now we've moved up to 2.06, 2.44, and there's the phase change at 2.24, and it remains balanced with the same capacitance, which is good. shows we got the balance well optimal to begin with. It's maintaining that balance as we change the coupling. Okay, so this is 15 millimeter spacing. Coupling will be down less than 0.1 now, I should think. All that remains the same. Okay, good. All right. Come back to continuous sweep. See how our balance is looking. Pretty good still. Okay, I'm going to continue to take it further and further away. Sliding it further and further. As we can see, the balance is now going out between the upper and the lower. We'd have to retune using the vacuum variable capacitor in the primary to recover that. So let's get that to about there. Let's do that. So I'm just going to change that balance a little bit. It's just a very small adjustment. So about there. There, we've rebalanced. I'm going to pause it there. Have a look at the distance between the coils, which is now about 22 centimeters. Just check the balance between them. Yes, it's not bad. Okay, let's move the markers in because I want to store this result. Okay, there we are. So now up to 2.1, down to 2.33. As you can see, it's all starting to collapse onto the phase change, the central phase change here. But remember, this is an interaction between the primary and the secondary. When the secondary coil goes out of coupling, then we'll see it revert just to the primary situation, which we're getting close to now. I'm going to show that in detail. 1 magnitude of continuous phase. That's now moved out to 22. I also changed the tuning capacitance slightly to rebalance. I'm just going to measure what that is. Okay, so just setting that to measure. 603.8. So 603.8. I think that's all right now. Was enough to balance the upper and lower resonant frequencies. Nope, wrong. There we go. Save that one as well. Remove the LCR meter. And we'll just take another scan, make sure we're still looking balanced. Yep, that's good. Okay, so I'm going to put it back in continuous, and we're going to continue now moving the secondary away. Collapsing still 4. Balance is okay. Still sliding away the secondary. Let's just check the distance now. 30 centimeters. that's at 30 centimeters. Let's keep going a little bit more. There, collapsing, collapsing. The secondary will go out of range quite soon. So that is now 45 centimeters away. Still going further and further. It's almost completely gone now. The influence from the secondary. And we would discover there that the secondary is almost out of influence, and it's 70 centimeters, a little bit further. There, gone. That is now almost 90, 88 centimeters, showing just the primary parallel peak left. Interestingly enough, that's also exactly on where we were busy in the middle with our phase change.